This is Professor Antonio S. Marahas, and this is Advanced Digital Technique. Okay, so our discussion today is about combination of gates. So, combination of gates are types of gates combined or connected together to represent a Boolean equation. So, for example, we have here an equation AB plus AC is equal to X. This is our Boolean equation. So how do we represent this Boolean equation using our gates or logical circuit? So if you notice that your AB here can be represented by an AND gate. So if you remember that our AND gates has two or more inputs, you have, say, for example, inputs A and B, and the output is obtained by multiplying A and B. No? So you have your A and B, so we represent that with an AND gate with two inputs, A and B. Of course, the output of this AND gate is A, B. Okay? And then we have here another AND gate with inputs represented by A, C. So we have here another AND gate. So we have inputs A and C. So the output of this AND gate is A times C. And these two AND gates are being OR together using an OR gate. So we draw an OR gate. So that is your output X. So X here will be equal to AB plus AC. That will be our logical circuit representing this particular equation. So how do we obtain the truth table for this particular logic circuit? So we have here the truth table. Again, we have inputs A, B, and C. You have A, B, and C. Okay? And then the output is represented by X. So again, the combinational values of A, B, and C are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay? So how do we obtain the value of your X? All we have to do is to substitute the value of your A, B, C into our logical circuit. Okay? So in this case, your A, B, and C are 0. So this one here is 0, 0, A is 0, and C is also 0. So for the AND gate, if you review our discussion on the different types of gates, it says that if any of the input is 0, then the output is 0. That is for the AND gate. So since you have 0, 0 here, so the output here will be 0. And then for your AC, here you have input 0, 0, so the output here will also be 0. Then we have here an OR gate. So the OR gate says if any of the input is high, then the output is high. But since all inputs here for your OR gate is 0, then the output of your X here is also 0. So you place it here. Then we change the value of your C for the second condition, 0, 0, 1. So that means that C here is already 1. But then, your AC here output will still be equal to 0. Because again, in the AND gate, if any of the input is 0, then the output is 0. Or all input must be high to get a high output. So in this case, the output is 0. Your A and B is still 0. So your input for this OR gate is 0, 0. Then it remains 0. So you put it here. Then you have 0, 1, 0. B is now equal to 1. So even if B is equal to 1, the output here will still be 0. Okay? And your C here is 0. So you have 0, 0, still 0. Okay? Then you have 0, 0 for the OR gate. The output will still be 0. Then you have 0, 1, 1. So C is already 1. But A and B and C are 1, but A remains 0. So you have 0, 0, again, AND gate, 0, 0, 0, 0. So for the OR gate, the output remains 0. Then you have 1, 0, 0. So your A now is 1. B and C are 0. Okay, so again, 1, 0, still 0. 1, 0 for AC, 0. The output of your X after passing through your OR gate will remain 0. Then you have 1, 0, 1. 1, 0, and then letter C is 1. B is 0. Okay? So you have 1, 0 again. It remains 0 here. Then we have here 1, 1. All inputs are high. So the output is 1. Okay? And based on our definition for the OR gate, if any of the input is high, then the output is high. Okay? So the output here is 1. Then for 1, 1, 0, you have here 1, 1, and then C is 0. You have 1, 1, AND gate. All inputs are high. So the output here is 1 or high. Here, you have 1, 0. The output here is 0. So, OR gate again, if any of the input is high, the output is high. So, you have here 1. And if all inputs are high, A, B, and C are high, then you have A, B is high, output is high, A and C is high, so the output here is also high. Any of the input is high, the output is high. So this will be our truth table for this particular circuit, no? Based on our logical equation. Now, we can also draw an equivalent circuit of this in which all inputs of the same variable are interconnected. For example, you have A and A here, so you interconnect A and A. Okay, so you will have only one input A here, and then you have B, and then you have C. Okay, so you have three inputs A, B, and C. That is how the logical circuits are drawn, no? So that's it for this particular example. Okay, so we go now to example number 2. We have here a new equation. We have AB plus C complement is equal to X. Okay, again, AB here, if we will represent this with our logical circuit, AB is represented by the AND gate. You have inputs A, B. So the output here is AB. And then it is being ORed to C complement. So you draw an OR gate. Okay? And that is one of the input if your OR gate is AB. And the other input is your C complement. So you have here C. Okay? Now, it is complemented. In other words, you can use an inverter. Like that. And this one here is your C. So the output here is C complement. Okay? So the output now becomes AB plus C complement is equal to your output X. Okay? So the table will be again obtained using the same procedure. So you have the truth table. You have A, B, and C. Then you have output Y, or X, I mean. So, combinational values of A, B, and C. You have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So what are the output, what are the values of your X with this particular values of A, B, and C? So again, we have to substitute the values of A, B, and C into our logical circuit. So you have 0, 0, and C is also 0. So you have A, B, OR gate. The value here is 0. I mean AND gate. The value is 0. Then you have C, which is equal to 0. Once it passes through an inverter, it becomes 1. No? So the value of your C is 1. So that for the output X, you have 0, 1. And the OR gate says if any of the input is high, the output is high. So you have here a high value. So the output X here is 1. So 0, 1 is equal to 1. Okay? For the 0, 0, 1, 0, 0, and this is 1. Again, this is 0 for the AND gate. Then 1 here, invert, this becomes 0. All inputs of your OR gate is 0. So therefore, X is 0. Then 0, 1, 0. 0, 1, and 0. Okay? So you have A and B again, 0. You have C is 0, invert that, this becomes 1. So one of the input of your OR gate is 1. So X will be equal to 1. So this is 1 here. And then you have 0, 1, 1. 0, 1. C is 1 also. So you have 0, 1 is 0. 1 invert, this becomes 0. 0, 0 for the OR gate is 0. So you have 0. Then you have 1, 0, 0. So you have 1, 0 again. A, B is 0. C is 0. Invert that. This becomes 1. Okay. So one of the input of your OR gate is 1. So the output here is 1. So you have here 1. 1, 0, 1. 1, 0, and 1. So again, this is 0. C is 1. Invert. This becomes 0. 0, 0 is 0. Then you have 1, 1, 0. You have 1, 1. The output is 1. or input must be high to get a high output. Then C is 0, invert that, this becomes 1. So you have 1, 1, the output is high or 1. And for 1, 1, 1, you have 1 for AB, and C is 0. You have 1, 0, the output is still 1. And that is for the equation AB plus C complement is equal to X.